This section and video will cover the beginning and introduction to our course, and we'll be starting with functional groups, and we kind of have this divided into 4 sections. And for this first one, we're going to be talking about some basic definitions, what we're talking about when we talk about functional groups, as well as some certain nomenclature conventions. And then we'll get into some information about acidic functional groups. So when we talk about a functional group, it's distinct from what we talk about like when we say the names of different types of what we call just general groups that are like added or portions of a molecule. So for example, a methyl group or an ethyl group is not a functional group in and of itself. They're representative of, as it turns out, alkanes, because both of those are hydrocarbons. So when we talk about functional groups, we're talking about portions of a molecule that are responsible for the physical chemical properties of that molecule. Now, usually any type of a drug molecule usually has multiple functional groups, and each one has their own properties. So the overall properties of the group are based on not only the number of these different functional groups, but also their arrangement in three-dimensional space. Because as we'll talk about later, arrangement in three-dimensional space of various types of electronic structures is how different molecules recognize one another. So we'll be talking about that later when we talk about molecular recognition and molecular interactions. So this is just a subsection, a little picture of part of some of the functional groups that are on your handout for the functional groups that you're going to be expected to know a variety of these. And so let's just get into the general aspects of nomenclature. Here are some references about nomenclature if you really want to look something up and have some questions about it. For the most part, you're not going to need to know things in the type of detail that maybe you had to know them in organic chemistry class, or if you were in graduate school in chemistry, this type of thing. So you probably may not need to refer to these, but the links are just there should you ever need them. But you should be able to name functional groups, stereochemistry, conformational names, as well as certain simple types of structures and names. Okay. So when we have drugs, there's a variety of types of naming systems that are applied to drugs. First of all, there's the chemical name. All molecules will have a chemical name. And the structure, how the basically atoms are attached, the number of them, the types of atoms that are in there, all of those basically go into the structuring of the name. And there are various types of systems that we have for doing that. So rather than just having each individual discoverer randomly come up with names, there have been various types of conventions and groups of people who have gotten together and developed systematic naming systems. So one of these, UPAC, that you see here, IUPAC, is the International Union of Pure and Applied Chemistry. That is what's considered the gold standard, and if all else fails, what people should or need to refer to. But it's not, in many cases, commonly used because simpler naming systems often serve the purpose better than the UPAC name. So we'll show some examples of this. CAS is Chemical Abstract Services. That's another big one, and there are others as well. In fact, individual chemical catalogs often use their own type of a naming system. Then we have the common name or historic names of various types of compounds. So common names, you can think of something like aspirin or morphine or atropine, these types of things. And those things are very commonly understood, and you can just easily use that name and find everything else you need to know about those types of compounds, because that's typically how we refer to them. Historic names were sometimes at one point a common name for a material, but have kind of fallen out of use. So things like carbolic acid. Carbolic acid is what we now know just as the group phenol, which is a 6-membered benzene ring with a hydroxyl group on it. And since that hydroxyl group is on an aromatic system, it actually has a different characteristics than a typical OH group, as you would find in an alcohol. So we actually consider that a separate functional group. Anyways, it's acidic, and hence it had the name carbolic acid, but we don't use that anymore. You would rarely find that unless you looked at some old type of a text. Okay, then we have code names. Code names are basically can be any kind of a random thing that essentially a company decides to use for its own purposes to refer to a compound. So what it amounts to is when a chemist makes a compound for, working for a company, they want to put it into their own cataloging system. And a lot of times these are very simple catalog systems. You can think of it as a file folder, and that file folder just has a number on it. So that's often what these things are. They are just simple numbers. You could logically think that, if you make one compound, then you make the next, you would put them in sequential order, but companies decided to randomize these numbers when they discovered that their competitors were using that information to basically decode the thinking of the scientists in terms of which compound was made first, which was made last. So this is the direction they're going. So randomizing the numbers fixed that situation. Okay, then we have our generic names. There is an organization which a pharmaceutical company would submit their new compound that they're trying to develop to, that USAN, and that organization will assign a name to that drug structure. Now, the manufacturer can suggest names, but it has to conform to certain standards that USAN has. And what USAN says will generally be what stands and what will go. I mean, you can object to it, and there's probably some back and forth, but for the most part, they have the final say on what the generic name will be, not the company itself. Okay, then there's trade name that is specific to the manufacturer. So they will use that for marketing purposes. And in fact, one generic drug, one drug that has a single generic name might have more than one trade name. And part of that has to do with it can be either a different formulation, or it can actually be the same drug but used for a different use, a different medical use. So they use the different trade names to market to different classes of physicians, right? A person's a specialist in cardiovascular versus one in women's health, for example. So that type of thing. Okay, so in chemical naming, as I mentioned, there are several systematic types of systems, and we're showing two of them here side by side. So we have the UPAC or the CAS system, which is shown in red here. And you can see in many cases there's a lot of similarity, right? For the first one, pyrrole 2-carboxylic acid versus pyrrole, acetic acid. Okay, so a little bit different. And actually the numbering is opposite for these, because the carboxymethyl is the acetic acid part, and the 5-carboxy is the 2-carboxylic acid in the UPAC name. So depending on how they do this, they even are numbering these groups differently, right? So when we say pyrrole 2-carboxylic acid and then 5-carboxymethyl, that's this side here. But in the CAS system, we have our pyrrole, and we're saying 2-acetic acid and 5-carboxy. That's because they're using a different priority system based on the substituent. CAS system has this very odd kind of proclivity to want to call everything an acetic acid derivative. And that's kind of where this comes from, because under normal circumstances, carboxylic acids get priority over any other type of substituent. So it's particularly in the UPAC system. So these types of things, it's just a set of rules, and when you follow the rules, you can end up with slightly different names. They both end up saying the same thing, and you will get to the same structure either way. And then sometimes there's just subtle semantic differences here. You can see how similar these two are. And then here we have naphthalene, 6-bromo, 6-bromo, 7-methyl, 7-methyl, 1,2-dihydro, right? So the only difference here, right, is the order in which they're presenting the groups. Some types of things do it alphabetically. Some of them do it based on certain priority rules. So in terms of how the order in which you'll list the substituents. So, I mean, these are the kind of details that we're not expecting you to really worry about the differences. If you saw this type of a name, or you saw this name, either one or the other, you should be able to understand that it means this type of a compound. Okay, and here we have basically the ring system, right, is given a different type of name in the two different types of systems. So this one is much less obvious between the two. Okay. So whenever we can, generally we try to use either common names or, in this case, generic names for many drugs, because that's commonly understood. We can easily reference this information and so on. As we can see, the chemical names in many of these cases starts getting complicated. And that being the case, if it's complicated, it's very hard to remember or use. Trade names, of course, are great, but then again, they're specific to a manufacturer. So any particular drug, which particularly if it has more than one manufacturer, will have the generic name and multiple trade names, right? So that can get confusing. So the generic names are kind of handy to kind of narrow things down in a sense. Now, this slide shows examples of a variety of these things shown together: common names, code names, generic names, trade names. So the type of name it is in the particular color code that's up top. So shown here, this nice little compound on the right here is commonly known as vitamin C, and you'll interchangeably see ascorbic acid as another common name for it. So it has more than one common name. This is an old compound, so it wasn't like something that came from a pharmaceutical company, so to speak. So there's no really code name for it. And we don't really have a generic name other than what we use the common names, since these are so common. It's kind of serves the role of a generic name. And then we have this compound here. Now this is much more complicated. It was made by the Merck Corporation. And when it was made by the chemist, right, they were looking at putting together this structure, and of course this is the name that basically a chemical naming program would come up with systematically. If a chemist sat down to name this using UPAC rules, this is what they'd have to come up with. And as you can guess, this would probably take a day's work from somebody. It's not that simple. You have to be very careful. There's lots of, look at this, lots of stereo centers here, right? All of that has to be accounted for by, all of this nomenclature here, this alpha, alpha, beta, SS, and so on. All of that is relating to whether or not these protons are coming towards you or going away from you, this type of thing. So fairly complicated structure. So when the chemist submits this, and they say, okay, Merck, I made this, and someone wants to send it off to testing, they'll assign it a code number, and it gets this L645969 number. And if work is done early on in the development of this compound, that's often the name it will be published under as well, is just under that code name. Because they're not going to put this UPAC name in the title of the paper, right? In the title of the paper and in the abstract, they'll use this. This will exist down in the experimental section, right? The chemical name will be in the experimental section. But they'll say this compound is L645969 just by definition. And so that's what it'll go by until it gets farther along in development. Now, most companies just stick with one code name. Merck has this other practice, and partly it has to do with the size of their company, in that they have lots. As you can see, this is a big number. So there's lots and lots of these L numbers. So not to be confusing their publications and confusing their own people internally for that matter, when a compound goes into development and they're serious about it, they assign it a different code number that's simpler. It goes into this MK system, MK for Merck, and you can see it's a much smaller number. So it's much more selective to be able to get this number, and that just makes it easier to remember and refer to. So then papers later that come out from the company, right, usually in the development of this, the pharmacology of the compound and things like that, will be using this code number. And it is not until late in development when this material is submitted to the USAN folks to develop a trade name. Okay? And the USAN folks will often use either a prefix or a suffix. In this case, it's a suffix for the particular class of drug it belongs to. In this case, it's an HMG-CoA reductase inhibitor. All of those compounds end in the word statin. And you may have heard of statin drugs, right? And that's what they are. It's based on this suffix that's used. And all of the different HMG-CoA reductase inhibitors just have a different first half of the name. There's pivastatin, lovastatin, right? Simvastatin is this compound. So that's how it makes it easier, say, for the pharmacist to remember, oh, I see the generic name's a statin. I know what kind of compound this is. I know what drug this is, right? So that's the utility of that type of a system. Then, of course, the company itself wants to market it, right? And they want to market it. And of course, in the United States, we can advertise it on TV. And your average person looking at TV is not going to want to go, what's the difference between pivastatin and simvastatin and everything else? It all sounds the same, right? You get confused very easily. So they have cool little catchy names, trade names, right? Just like you have Tide detergent, right? Well, this is Zocor, and it's Merck's particular brand of HMG-CoA reductase inhibitor. And it's also, you know, physicians also suffer from the same information overload problem that everybody else does. So trade names, particularly when the pharmaceutical companies are basically having representatives coming in and pushing these things, the trade names often stick and are easier for them to remember and hence to prescribe. That's kind of how the system works. Okay, so we have trade names. So you can see how all of these different names have different purposes. So this is again just showing USAN. It's the United States Adopted Names Council. It's an organization and it's put together by people from the American Pharmacists Association, right? U.S. Pharmacopeia Convention, so Pharmacopeia, and American Medical Association. Those folks basically staff and make up this USAN committees or councils, right? That basically assign these names. And there are lists of these various types of stems. Now, in this case, we're showing suffixes, but there are also in some case prefixes that basically describe a particular class of drugs. So notice we're saying here, when we have a "phil" at the end of a name, that should refer to PDE5 inhibitors, which is phosphodiesterase 5. Okay? So, you know, they have like sildenafil, tadalafil, and so on. Those are the types of things you have there. And again, it just simplifies understanding, at least we understand the class of drugs. Now, not all drugs have universally these same suffixes, even if there's some in the same class. Sometimes there's going to be antibacterials, right? Some of which will have this suffix, some of which may not. Some of that's for historic reasons, you know, before a lot of this was systematized. But it's, for the most part, fairly systematic. Okay, so that's just general naming information. Now we're going to talk about when we have functional groups or heterocycles, which is essentially just kind of a different form of functional group. A cycle, right, is a compound that is cyclic, like, you know, benzene is cyclic, naphthalene. Hetero just means it has something other than carbon in it, right? It could have nitrogen, it could have an oxygen in it, or so on. So that's all a heterocycle is, nothing more than that. Okay, these types of things, right, can have particular types of properties, and they can have all kinds of different properties depending on what their composition is, right? So we can have either acidic materials, and we're using the Bronsted-Lowry definition, which is an acidic material is something that loses a proton, right? Gives up a proton, which is a hydrogen ion with a positive charge, which would then leave essentially a negatively charged material behind. Or we have basic materials. Basic materials are neutral to start with, but they will have basically like a lone pair of electrons, for example, where it can accept a proton. And then if it accepts a proton, then that whole molecule then takes on a positive charge, right? And when we basically protonate a base, what do we make? We make a conjugate acid, if you remember that terminology. In other words, it's that basic material now has a proton and a positive charge and is now able to lose that proton, right? Because all these reactions, neutralization and everything else, are reversible. And then our third type, so we have either acidic, basic, or we have compounds that are neutral. What do we mean by neutral? What we mean by neutral is if we are in water, right, the pH range, which is nothing more than minus the log of the hydrogen ion concentration, right, in the water, cannot be outside of the range of 0 to 14, right? There's a range at which we can have a certain number of protons in the water and or a lack of protons, essentially what you would often consider as hydroxide ions, right, which is OH minus. Okay, so it can just go within that range, but it can't go outside of that range. Now, certain functional groups, even if they have a proton, like an alcohol, can technically lose that proton under certain conditions, but the ability of it to lose that proton needs to take place outside of water. If we're in water, we cannot pull that proton off. We cannot get it basic enough in water to get that proton off of an alcohol. So we consider these compounds neutral. In other words, they won't be charged one way or another, and we can't pull off a proton or accept a proton on them. Okay, so those are neutral compounds. And then of these types of compounds, right, acidic, basic, or neutral, we can have compounds that are polar, and you can have polar compounds that are charged or neutral. So actually, if we have an acidic compound that has lost its proton, or if a basic material that has accepted a proton, they will have charges on them, right? And so if they're charged, basically they are what we call polar. In other words, they will interact quite well with a compound that has a dipole, which is basically nothing more than the separation of the positive and minus charges in them. And so like water, for example, is such an example, because the electronegativity of oxygen is very different from hydrogen. So we have a kind of this distribution of charge within a water molecule where we have more electrons on the oxygen than we have on the proton, just in terms of how concentrated it is. So that means that these charged materials, right, like being in polar solvents like water, and so therefore would tend to be more soluble there. And then we can have neutral compounds that are polar. And so one good example of that is what we just talked about, which is alcohol, right? It can interact with water quite well, if you remember hydrogen bonding and things like this, but it doesn't lose a proton, so it doesn't get charged. So it is neutral, okay? So there are different types of materials which we can call polar, whether they're charged or not charged. Then we can have kind of the opposite end of that, which is non-polar things. And the real easy thing to think about there is gasoline, right? Gasoline doesn't like interacting with water, right? They separate from one another. And so we consider it non-polar. In other words, it is not something that interacts with polar materials, right? So hydrocarbons, alkanes, things like this fall into this category. And then we have other compounds in the middle that kind of might seem nonpolar, but they kind of might seem polar, but they're kind of a little bit in between, right? Hence intermediate. And some examples of something like this might be like ethyl acetate, which if you remember in the organic chemistry labs, if you did it, it's one of the solvents you can use that doesn't really interface with water very well, so we can use it as a separate layer to extract greasy materials into type of thing. But it is far more polar than just something like hexane. So in other words, compounds that have an intermediate level of polarity might be actually more soluble in ethyl acetate than they might be in hexane, which is completely nonpolar. So there's different uses for these different solvents and these different materials. They have different properties. So some of these things can also be described in different ways. Polar molecules kind of like being in water, right? We call that hydrophilic. Philic means like, to like, right? As opposed to phobic, right? We sometimes talk about things as being hydrophobic, right? And phobic means it doesn't like it, or technically it means fear of, but when you say have a hydrophobic surface, like wax, right? You put water on it and water will just beat up on that. Okay, and they don't like interfacing with one another. Whereas if we have a hydrophilic surface, like glass, for example, glass is a silica, right? So it's silicon atoms and hydroxide atoms all attached to it. And that actually can interact with water reasonably well, even though it's a solid and doesn't dissolve. But if you'll notice, basically most of the time, water will spread out on glass. And so like when it rains on your windshield, if you haven't treated it with something, right? So that's called hydrophilic. The opposite of that is lipophilic, which is something that likes interacting with lipids. Lipids are non-polar materials, right? So this is the type of thing that something that would dissolve, say, in gasoline, as opposed to, water, for example. So there are a lot of organic molecules that are like this. And then we have amphiphilic. These are compounds that have two properties. So sometimes one part of the molecule will be polar, right, and like water, and another part of the molecule will be nonpolar and want to be away from water. So the types of things that you have here are things like detergents, lipids, fatty acids, things like this, fatty acids make up detergents, right, and things like that. So in other words, they can interact with both water and greasy things, and they do so separately for different parts of the molecule. Okay, so amphiphilic. And proteins can also be amphiphilic in terms of how they work. For example, certain proteins that you have on your lipoproteins. So you may have heard of HDL and LDL right in your blood, which are just basically lipid particles. And on the surface of them are proteins, and they are amphiphilic proteins, which means half of the molecule basically interacts with the lipid in the particle, and the other half is facing out towards the water. And so hence they have those dual properties. Okay, then we have other properties. So nucleophilic, technically something that tends to be electron rich. And we can think of it as attacking things that are electron deficient, and we call those electrophilic. Okay, so what do we mean? So electrophilic is probably easy to understand. Electro, right? Think of electrons, right? And it likes electrons. So it means it's basically deficient in electrons and it wants more of them, right? And this is the opposite. So what does it mean? It's rich in electrons, right? And it wants materials that are deficient in electrons. So you can think of the nucleus, right, of an atom as opposed to the electrons around it. So we think of nucleophiles as often negatively charged or very electronegative atoms that attack sites on molecules and can do things like displace halides or other things like this. So you've heard of reactions that are nucleophilic or electrophilic reactions. We're not going to be talking about reactions in these terms specifically in terms of the exact names for those mechanisms, which if you remember are just odd things like SN2 or SN1. We'll be talking about this is a nucleophile and it attacks this. That's kind of the limit at which we're going to be using this terminology. So all it means, again, this is electron rich, this is electron deficient here. And so that ties into what we're talking about here. Functional groups can either be electron rich or electron deficient, having to do with the number of double bonds they have, whether they have explicit charge, and whether or not they have electronegative atoms in them. Okay, and then finally we have something that's kind of independent of all these other properties. We have compounds that are either stable, which means that nothing much happens to them. In other words, you can put this material in a jar, sit it on a shelf, and 100 years later it'll be there, right? And things that are stable are, real simple things like sodium chloride, right? Table salt. Nothing's going to happen to table salt. It might degrade the bottle it's in, but nothing's going to happen to it. So, because table salt's corrosive. That's the only thing with regard to that. Now, labile is the opposite, which basically means it's not stable. In other words, you put it in a jar and it's got a shelf life. So you come back months later and something will have happened to it where it's degraded. Like, for example, diethyl ether, a common lab solvent that we have. Once you open it up to the air, you need to use that material within a year, because what tends to happen is it can tend to form peroxides. These peroxides can actually be flammable and explosive. So it can be a little dangerous working with old cans of ether and such. Or other things which are just plain reactive, whereas if you open it up to the atmosphere, it'll react with the air or the moisture in the air, something like that, and actually react with it. So that's what we call labile. Okay, so just kind of summarizing many of the types of groups that we'll be talking about in terms of polarity. If we're talking nonpolar, remember we said these things are like greasy, like gasoline. So those are your alkenes, right? I mean, how do we define gasoline, right? We talk about it in terms of octane. Octane is kind of an ideal fuel, and it's an alkane. And so that's what it is. It's very hydrophobic, right? Gasoline does not dissolve water, only to a very small extent. And it basically, if you put it on the ground, say on a wet surface, right, it'll float on the top of it, right, and give you that cute little, very pretty monolayer with the blue rings and all that good stuff. And that's also why you don't use water on a hydrocarbon fire, right? Because it'll cause that hydrocarbon to spread across the surface of that water and just spread the fire. Okay, so that's nonpolar. And alkenes are simply alkanes that have a double bond in it instead of all single bonds. Alkyne has a triple bond in it somewhere. Aromatic hydrocarbons, we'll talk specifically about what aromaticity is, but think benzene, stuff like that, are aromatic. It's just a particular form of stability that occurs in cyclic molecules that have a particular number of electrons associated with them. And thioether, it's just another example of something where the sulfur is not much different than a CH2 in the alkane. So again, it's just another greasy material. Okay, intermediate, we talked about some of these. We talked about esters, right? Carbonates, one we haven't talked about, thiol, sulfoxide. These are all going to be in your list, and we'll mention these when we get to that particular type of functional group. Polar groups, so amines, alcohols, phenol, amide, urea. These things typically have oxygens with lone pairs of electrons that can basically form hydrogen bonds with water, or they have heteroatoms, oxygens or nitrogens, that have a proton on it that can actually donate that proton to a hydrogen bond and hence interact very well with water. So these are hydrophilic typically. And then we have charged groups, and there's a variety of these. Amines are bases, so we can put a proton on it, and then it's called an aminium. The IUM indicates that it's an ion and it's positively charged. We have guanidine, which if protonated is a guanidinium. We have amidine, which if protonated is amidinium. We have carboxylic acids, which if we remove the proton, we call carboxylates. We have phenols, remember, which is a benzene ring with an OH on it, and if we remove the proton from that OH, we get a phenolate. A sulfate is, think of something like sulfuric acid, but if we remove a proton, it becomes a sulfate. And similar for a phosphate, if we have something like phosphoric acid and we remove a proton, it is a phosphate. So this I'm just going to leave for you as informational, kind of talking about some of the weird stuff that we have with intermediate polarity compounds. The main point of this is kind of what's in color here in the middle, in that we can have compounds that are hydrophilic and we can have compounds that are lipophilic. Okay. Now, if something is hydrophilic, it is not necessarily hydrophobic. Often we think of that is the case, like for example, hexane. Okay, it is lipophilic. It likes lipids because it itself is an alkane, and it is also hydrophobic. It doesn't like being in water. But there are some lipophilic compounds here, lipophilic, right, like tetrahydrofuran, which is a 5-membered aromatic ring with an oxygen in it in one of the positions. And it perfectly well dissolves in these other types of nonpolar compounds like chloroform or hexane, right? It's miscible with those. But it also dissolves in water. It is hydrophilic. Okay, so it has both of these properties, which are actually, one of them is opposite of these materials, right? So just because something, right, is itself greasy, this you can consider it greasy, right? Because, oh, it's lipophilic, right? But, oh, it's also hydrophilic, whereas these are hydrophobic. So just because you have one does not predict that it is necessarily the opposite of the other, right? So in other words, a hydrophilic compound is not necessarily lipophobic, right? It's or lipophilic. It could be either. And we don't usually talk about the word lipophobic, but you can consider something that doesn't like dissolving in lipid as lipophobic. It's just not a common term that people use, right? But you can consider basically very polar compounds, right, as that, since they don't interact with these lipid type of compounds. Okay, like water, for example. Okay. So now getting into the actual acidic groups. Now, I refer to a book here that you don't have access to in the library. It's a small book by Lemke on functional groups. It's a very short read. It's very good. Not too expensive to buy, but you're not required to have it. So, but I refer to it just for reference because it's something that people often commonly have. Carboxylic acids are basically a compound, typically some type of alkyl group, right, attached to a carbon that is double bonded to an oxygen. So you'll often hear the term carbonyl group. But a carbonyl is not a functional group. It's kind of a substructure within other functional groups. And then it's got a single bond to an OH. In reality, this is a resonance structure. You could have the proton up here or down here, and you can have this double bond here or here, right? And it can kind of go back and forth between those. So in a sense, really the proton is kind of shared between these two oxygens, and the double bond is kind of partial, and it's between the two oxygens in a sense. So we have here this planar molecule that we call a carboxylic acid. It's an electron withdrawing functionality. So in other words, what does that mean? It means that it pulls electrons towards it. So if you have another group over here, right, in this R region, right, electrons could be pulled from that R group, which could influence the properties of this R group. Okay, so that's what we mean by an electron withdrawing functionality. It's polar, right? It likes water. These things can interact with water quite well. It's acidic. This proton is lost at a pH of about 5. This will be half protonated. So it'll be half minus charge and half with the proton on it. That's kind of the definition of what a pKa is. We'll talk about this when we talk about acids and bases. But essentially, this is an equilibrium constant for where we have equivalent amounts of the protonated and deprotonated form. So it equals the pH where we have 1/2 of this and 1/2 of this without a proton. Okay? That's the technical definition of what this is, a pKa of 5. Okay. The groups, so if this R group has a carbon here, and it has a proton on that carbon, the electron withdrawing nature of this carboxylic acid is not strong enough to make the proton on that carbon acidic. So it is neutral. So a CH2 group or a CH something or other group here will be neutral. Okay? We'll talk about where the exception to this occurs when we talk about active methylenes in a few slides. Then we have here, it is a hydrogen bond, often called just an H bond, hydrogen bond acceptor. It accepts a proton, right, from another heteroatom that is covalently bound to that proton, right? We'll talk specifically about what all of these means in a lot of detail later, but that's what we call it, being an acceptor of a hydrogen bond, and it's a donor to a hydrogen bond if the proton is still on here, right? If it is ionized, meaning that the proton is already removed and all we have is a minus charge here, it doesn't have a hydrogen to donate. Then in that case, it's only an acceptor. Okay, we'll talk about this when we talk about hydrogen bonds. It can be involved in ionic interactions, which means charge-charge interactions, and it can form salts. And that's a very common thing. Drugs, when we sell them and store them, are often more stable if they're in a salt form. So it's very common for acids to be various types of salts and for bases to be various types of salts. So a common type of salt you might have for a carboxylic acid is, say, a sodium salt or a potassium salt. And so it would be some, let's say we have acetic acid. The sodium salt of that would be sodium acetate, where the only difference is we have a sodium ion instead of a proton here. Okay, and that is a salt. It is hydrophilic, right? It likes water, which we know, we've already talked about that. And it's a stable group. In other words, it's actually at its highest oxidation state. Usually we have a lot of instability if things can interact with the air and oxidize. This cannot. It cannot be further oxidized. So it is perfectly stable. In fact, you'll see in most metabolisms we get, if a carboxylic acid is possible, it is often the observed end metabolite that we see. And it can be involved in metabolism. It can be metabolized, but only with the phase 2 type metabolism. We'll talk about when we talk about metabolism, we'll talk about the difference between phase 1 and phase 2. So phase one is, you can think of it as a chemical reaction where we change this, say, to a different oxidation state. That does not happen with carboxylates. Phase two means we basically add something to it. We couple something to it. That does happen. In fact, what usually happens is the sugars get put on here. We call it glucuronidation. It's a particular type of sugar that gets transferred onto this. So that's kind of all the different things and features you have with a carboxylic acid. And I know you don't understand every bit of this right now, so think of this as kind of a summary sheet of things that eventually, by the time we're halfway through this course, you're going to know every bit of this, okay? Because we're going to talk about it at different stages as we introduce these different concepts. Now, acidity varies based on a variety of features, one of which is if an electron, right, in an ionized compound, so in this case, each one of these is ionized, this is an alcohol that's ionized. Remember, we said we can't do that. We'll talk about that. Carboxylic acid or a sulfate. The difference between the three of these is this minus charge exists on one atom. This one exists on, actually it's three atoms because it's spread out on this oxygen, carbon, oxygen. The minus charge is spread out. This minus charge is spread out over the three oxygens and the sulfur, right? So it's much more spread out. That being the case, the proton on this methane sulfonic acid, right, can be lost very easily. In fact, in water, methane sulfonic acid doesn't exist in the protonated form. It is completely ionized. And if something is completely ionized, we call it a strong acid. So notice the pKa here, this is the pKa number, is a minus number, which means it's less than 0. So when we get into water, which can only be 0 to 14, that means there are no protons on here. It is completely ionized. That's how you interpret this. Now our carboxylic acid, remember we said it was about a pKa of 5, so 4.74 here for acetic acid in particular, happens in the middle of that range, right? 0 to 14, right? Well, roughly, but I mean just in general, it's within that range. So we can have both protonated, this acetic acid form, or this acetate ion form. And if we are at a pH that is less, in other words, we're in a strong acid solution, we're going to have more of the protonated form of this. If we go to a higher pH, say pH 7, we're going to have almost all acetate ion and really hardly any acetic acid. So we're going to talk about how to actually calculate and estimate how much of each form you have at different pHs, but that's the concept of what we have here. If we're exactly at pH 4.74, we have equal amounts of this protonated acetic acid form and equal amounts of this acetate ion, 1 to 1. Alcohols, remember we said, oh, we can't do this. We can't get this ethoxide ion. It's just not stable enough in water. And what happens, it exchanges with the protons in water so rapidly that all we get is ethanol. The pKa of this is almost 16, which means that between 0 and 14, it is always protonated. So we call it neutral, okay? In organic chemistry class, you might have talked about this type of thing. We don't have this in the human body. This cannot exist in water. All we have is this. And so that's why we want you to know this as being neutral, realizing that this is, in the case of water, is what we're talking about. This is just some other natural materials that are carboxylic acids. Cholic acid, which is a metabolite of, say, cholesterol, for example. Abiotic acid, biotin, citric acid, niacin, pyruvic acid, malic acid. All these are various natural materials that notice have carboxylic acids in them. So it's very common in biomolecules. Now, in a lot of cases, these carboxylic acids are modified in such a way that they're not acidic. So we have different functional groups. Here we have esters, right? Here it's actually tied up in a heterocycle. I really don't want to call this an amide. This is an amide here. This nitrogen double bond to carbon and oxygen. Since this is in a heterocycle, this is actually aromatic, so the resonance forms of this show that these are not amides, and we're not going to discuss that at this moment. But the point is that you can consider this originally came from a carboxylic acid and it's been derivatized. This is an ester, and this is an anhydride. So this is basically two acids where we've removed a model of water between the two of them and basically made this anhydride compound. And this is an amide, much as you'll find in the peptide backbones you might have learned in biochemistry. Okay, so these, though, none of these are acidic. They're just derivatives of carboxylic acids. Now, there are other types of groups other than carboxylic acids that are acidic, one of which is an imide. So an amide, right, is like half of this, where we have just this nitrogen carbonyl group. And if we put another one on the other side, it now is also electron withdrawing, and it makes this group more acidic, where now our pKa is in the 0 to 14 range, and our pKa is around 8. Now remember, we said carbons with hydrogens on them that are next to carbonyl groups are not acidic. But if we have two of these things, right, each pulling electrons away in each different direction from this central CH2, right, it makes it acidic. And in this case, with the cyclic molecule, which we call Meldrum's acid, it's about 5, which is very similar to a carboxylic acid. If it's not cyclized, you can see this is a very similar compound to this, but it's not cyclic. Here, notice the difference in the pKa. It's quite different, even though this is still a little bit acidic, right? 13, it's not very acidic, but it is a little bit. So big difference whether or not the shape of the molecule we have. And there are reasons for this with regard to this creates some hindrance to this position where the protons are because of the way this thing can rotate. This is where everything is forced and tied back. You know, think of like a ponytail, right? You're not going to get hair hanging in your face, whereas here you could, type of thing. That's kind of the concept of what's going on there. Okay, then we have sulfur derivatives, many of which are neutral, so we're not going to be involved in that here in this acidic talk. But we have thiols, otherwise known as mercaptans, and so either of these two common names are used, and that actually has a pKa of around 10. Or we have sulfuric acid, which of course you're familiar with, which is a strong acid, and if one of these OHs is an alkyl group instead, so it's instead of SO4, it's SO3, that's called a sulfonic acid. Doesn't matter, it's still a strong acid. Okay, so this proton comes off of here very easily. Okay. We have phenols, which remember we said are aromatic rings that have an OH on them. pKa is roughly around 10. So not highly acidic, but remember what I said, the compound phenol itself used to be called carbolic acid. So it is corrosive and it is acidic. So that's a feature that you should know about that.